Okay, so today I'm going to talk about the code implementation of the priority queues. So that is the topic we have been talking for the last times. So now that is the next talk, and I'm going to show the code implementation on Java of the priority queue using a binary heap. Using a binary heap. So yeah, today I wanted to explain this code. Try to explain this code. Yeah. So initially, before we'll create the class, the class of the data structure of binary heap, and using which we want to implement a priority queue. We need to import some libraries, that is the ArrayList, also collection and list. We'll need these data, these libraries a bit further, and now we have just to import them before the class. And now we want to create a class binary heap that would also have the generics. It would have the generics. And also we need to make it comparable, because a bit further we'll need to compare the elements of it. So for example, we'll need to compare it at the moment when we have to bubble down elements or bubble up. So to add elements, we'll need this comparable. So it would be very important a bit further. And now we have just to extend this class with comparable feature. And now we want to create a list, a dynamic declare a list, a dynamic list to track the elements inside the heap. And this way we'll we'll track the elements. We want to declare heap list, and also we want to make some constructors. So this means that if the user would import different types, for example, empty this parentheses, empty brackets, or with the initial size, with the initial capacity, or for example with the elements, we will need different constructors. So the first constructor is the construct initially empty priority queue. That would be empty. And that's pretty simple. So now the next type of constructor is a priority queue with an initial capacity. So here we would be provided with it. So the user would import the priority queue, the capacity, the initial capacity of it, and we'll create the array list. The heap would be equal to the array list with the size with a given size. And next, there is another way to construct it, a priority queue that is using heapify and O of n, or linear time complexity. Here we would be given the elements or lamps, that is the list array, and we want, so initially we would declare the heap size variable that would contain the length of the lamps array, and next we would assign the heap list equal to new array list with the size of heap size that we have, the variable that we have just declared. And next we want to place all elements in the heap, So to do this, we can just traverse through every or loop every element in the lamps and to add them. So while we can say so, we would add the 1 to the I, that is the counter, until or while I is I is less than heap size. We would every iteration we would add some heap to some element to the element no, an element from the heap, the element with the index of I to the heap, and next we would do the process known as heapify. So that would take the linear time, the O of n time complexity, but that is the best way to make a priority queue from the array. So that is a bit complicated thing, but it is, I think it's not very difficult. So here we are looping every element before where I is the math, that is the maximum value of 0, and heap size divided by 2 minus 1, that is the heap size. So divided by 2 minus 1 is the formula for the parent node, provided by, so if we're provided with the children node, we can know in this way the parent node, and we would sync every node until I is greater than or equal to 0. We would sync every node. So this way, using a sync method that we would create a bit further, we would do the heapify process, and this way we would create a binary heap or a priority. We would provide a binary heap with given or with inputted the array of elements in it, and also there is another constructor that is with the collection of elements. So in here that also runs in a time complexity of and a time complexity of O of n, and in this way, in this time, we are doing the same things. We're creating the ArrayList with the size of heap size. That is, by the way, now that is the size of the LAMs. LAMs variable. And now the difference here is we're using add all method. Add all method, and that is also runs in a linear time because we have to add every element. And next, we will do the same heapify process. So now we want to build. We want to create some other methods that we'll need to implement a priority queue using a binary heap. So now the first method is empty. So we're returning if there is a Boolean value, and if the size of the heap, if the size is equal to 0, that means it is empty, and we want to return true. Otherwise, we would return false because the size is not empty, is not equal to 0, and we are going to write look at the size function a bit further. And now we want to make a clean method that would cleans everything inside the heap, that would run in a linear time complexity, because we'll need to clean the heap, and through that we need to traverse through all the heap. Yeah, and now the next is the size, that just works just using the size yeah, size method. So this size method is a built-in function, by the way, to this ArrayList data type, data structure. And now the next method is peak. So if we want to return the value of the element with the lowest priority in the priority queue. So of course, if the priority queue is empty, we will provide the null. Would return null, because there is no value on the peak. By the way, there is a null value on the root node on the peak, and that's why we would return null. But otherwise, we'll just get the element with the index equal to 0. With the index 0, we would get its element of this index, and in this way we would get the root node, the element with the lowest priority. And next we want to write the poll. The poll is, by the way, remove at. So the poll is to remove the element with the index of 0, or remove the root node. And so we would just use the remove at function. That's pretty simple. And remove at, remove at. And next is the boolean value. Would provide a boolean value of where the function contains, where the method contains. So we would given a lam with the generics type of this lam, because we want to for our priority queue to contain different data types, and for this reason we would use generics here, and we would do the linear scan to check the containment, or to check if an element is in the heap, and this would run in the time complexity, in a linear time complexity, and time complexity of O of n, because we need to scan. In the worst case, we'll need to scan through the whole array, through the whole heap. Before I is less than, until while y is less than size. The size that we have just looked, at, and if the value of the index I is equals lam that we want to find, that we want to check if it is in the heap, would return true. But if during our traverse, during the loop, in the while we're traversing this array, this heap, if there is no element, that means that we haven't found it, and it doesn't contain in the heap, and we just return false. And now the next is add. So there's void. So we don't need to return anything here. Void. So if we want to add element to the priority queue, but the element must not be null, because we want to throw exception, a legal exception if the element is equal to null, but otherwise we would add it to the lam, and the index and the last lam is equal to the size of the heap minus 1. And now we want to use swim. So swim is the same as bubble up, that we have looked at it in previous talks. That is the index of the last element, and we would make the method to swim this, or bubbled up, because if we're adding, we can't bubble down or sink the element at the last layer, but in this way we can only swim it or bubble it up. And also this method last would provide the Boolean value. So this task, if the value of node I is less or equal than the node j. So also this method assumes that I and j are valid indices. So this is the internal method for this array, and it would be private because the user don't need to compare these elements inside the class. Yeah, so that is for just for a simplicity here, and so we would get the index of. So we're given the indices I and j, and we would we'll want to get the element on the I position, on the I index, and on the j position, and would compare that. So we would use for this compared to. So if node 1 compared to node 2 is less or equal to 0, we would provide true. So otherwise, if it is greater than 0, if it is 1, we would provide false here. That means I is not less or equal than the node j. And now we want to create another private method here, that is swim, that would input the index k, for example, and we want to know the parent of the next the index of the next parent node. The parent node of the k. So that we would use the formula for this. That is, we know that the formula for the child node is plus. No, we have to multiply I by 2 and add 1 or 2. So here we would just first subtract 1 and then divided by 2. So in this way we would know the index of the next the next parent node. And now we would create a while loop. Also while k is greater than 0 or node k is less than parent. By the way, the element on the index k and on the index parent. So if so, we won't swap them. But so if it is the element on the index k is less than the parent node, we want to swap them. And we won't write the swap function. We would look at the swap function method a bit further, but now we would swap them, and we would also swap their indexes. We would make the index of k equal to parent. And in this way we would continue to swap it with this parent node, so we would do this until the k, the element on the k node is less than on the parent. If it is greater, that means we need to stop swapping and it is on its place. And also we need to grab the index of the next parent node for the k. So we would do the same formula as here. We by the way, we are making the index of k equal to equal to the parent node, and the parent node is the next parent node of k. And this way, we would traverse within the pairs. Would traverse in the pairs of k node and the parent of the k node. And now we want to also to make a sync node, sync method that I think pretty similar to the swim node, but it would be opposite. Similar in this implementation, but opposite in its meaning and what this function does, by the way. So that is also private, and we need to know the heap size. So the heap size is equal to the size to the size of the heap, and while we are writing here true because we want to create an infinite loop, and then we would just break it. So we want to know the left node, the left child index and the right child index. So that is 2k plus 1 and 2k plus 2. And now we would assume that the smallest node is left, and because we need to create the smallest, we need to create the smallest variable, and we would assume that left is left is the smallest node between these two, of the two children, and we would compare. So if right node is less than heap size, and it is less than right, that means that the smallest in this case is the right node. So if we want to check if this node, this index is in our array, in our heap, and also if it is less than left. So if it is less than left, that means that the smallest node is left. And while we sync it, we would swap it with smallest node. And now so we are doing this in the while node, so we will continue to do it after. We will do the same these steps, and also we want to compare if the left node is greater or equal to 0 or greater to heap size, and yes, this is or symbols, and or k, the node at the k index is less than the smallest index. This way, this means that we need to break because we're outside the bounds of the tree, or we cannot sync k anymore. We don't need to sync k anymore because it is. By the way, we don't need to sync because otherwise we would break the heap invariant. We don't need to sync it anymore, and otherwise, if we have to sync it, we are just swapping it the smallest value and the k, and now we are declaring the k. We're setting k is equal to smallest, and so that is one. So these are one of the most important here methods for this binary heap, and the most complex, the most difficult. And so now also another private node swap, that is the function, the internal function that we need to do a sync or swim operation, that we're swapping two nodes inputted by their indexes. So we are getting the index. We're getting the the element on the I and j position, and just setting on the I index. We're setting the element j, the element that was on the j position, and on the j we're setting on the I. So in this case, we're swapping them. It's pretty interesting, I think. Algorithm how to swap them without additional variables and additional data leaks. And also, we need to do now a remove. And now remove is a public method, or the public, that means that the user would have the ability to use it, because the user, for example, wants to remove the element, and he doesn't want to, for example, swap the nodes. The swapping nodes is the private method, method. And so now we're checking if we want to remove the null value. We're just returning false, because we can't remove the null value. But otherwise, we're doing linear removing via search. Linear search by linear search, and that would provide the O of n, or the linear time complexity. Now we're traversing through the heap. So starting with the I equal to 0 until I is less than the size of the size of our heap, and would increase by 1, the I by 1 every iteration of the loop. And if the element is equal to the heap, the element on the index I at the heap, we would remove that. We would remove it, and would return true, that we handle to remove it, and otherwise would return false. That means that we cannot remove it because we don't know its index.
Yes.
Yeah, and now another private method is remove at. So we have done it we have done it a few times in the implementation. So by the way, that is pretty useful method. Yeah, and here, if the stack is if the heap is empty, we're returning null, because we can't remove it. We can remove anything from the empty from the empty an empty heap, empty binary heap. And now, so also an important note to make is that we're removing at a particular index, because if we're given a particular element, that would be the same as the remove method, but here we're given an index, and so we already know at which index where to find this, and we'll just it would take the linear, not the linear, but the logarithmic time complexity. That is that is of course faster than the linear, and it would be pretty fast. And so now we're declaring the index of the last LM variable is equal to size minus 1, the size of the heap minus 1, and now we are making the remove data variable, and we're getting the element at the position I. So that is the index of the element whether we want to. The remove data is the element that we want to remove. We are swapping the index of the last LM with this. We're swapping the last index at the last position with the element we want to with the element we want to remove. And now, as it is in the last position, we can just remove it. We can simply remove it without. We would remove it pretty simple. And now the also we're checking if the last element was removed. yeah. So if I is equal to index of the last lamp, where we're remove data, and now and also the lamp would be equal to the last value, and now we need to either swim or sink the element that was the last lamp that was this position before we have swapped it with the element we want to remove, where we're trying to sync it and we're using the sync function. But otherwise, if we did not handle to sync it because we don't need to sync it, it is on the right place. So we don't need to move it down. We have to move it up. So if we did not move it to so if the element of the node at the position of I is equals to the element, that means we want to swim it, and we already know how the swim operation works. The swim method works. We don't need to write anything else, and we would return the removed data, the element we have just removed, and now the is mean heap method. So that is so this method checks if the given min heap is a the given heap is a min heap. The given tree is a min heap. So this method is just for testing purposes. So yeah, it is needed to test if it is heap. It is a heap. So that is pretty interesting method. Yeah, and that is just to make sure the heap invariant is still being maintained. So where that is recursively, it recursively checks for if this heap is a min heap, and also we're calling this method with k is equal to 0 at the start of the root. So that means that we are we're starting our heap with the 0 node, not with the 1, because I think that's pretty strange to start with 1. And now, if we are outside the bounds of we need to check if we outside the bounds of the mean on the heap. So if we are returning true. So if k is greater than the heap size, we're returning true. And now we are getting the indices of the children nodes, the left and right child, and we're making sure that the current node k is less than both of its children, right and left, if they exist. So we want to check if they exist, and if it is less than both of its children. So if and we are returning false otherwise to indicate invalid heap. So this means if the child node is less than the parent node, that means that the heap invariant is satisfied, and otherwise we have to return false. That means there is not a min heap and there is an error someplace. We're checking if the left and right child in the heap, and if k is not less than left. So if it is not less, we're returning false. And the same thing with the right. So that means that is greater than greater than k is that means that the child node is not less, that the parent node is not less. So the current node must be less than both of its children, as we know. So if it is not less, we'll return false. And the same thing with the right. And we need to recurse it. So we're on both to make sure on both children to make sure they are also to make valid heaps. So we're returning true if the main heap is the mean heap on the left children and on the right children are both valid. So if so, we are just returning true. And if we are returning true, that means we handle to make a this heap properly. And now that is just the override. If we're to, for example, to convert it to string, and that's pretty simple. Yeah, it's obvious how to make it. That is the built-in function. And I think that's it for the implementation. It has 200 strings. Yeah, that's pretty interesting, yeah, code, and it's a bit complicated sometimes. But I think in general that is a bit that is not pretty difficult code. Yeah. Thank you, Robert.
Yep.
Robert. Oh,
That is complicated code. It is complicated code, but
yeah, a bit.
all right. Yeah.
Yeah.
Okay. All right. Well, thank you. Thank you for a good video. So you're
Thank
now
you.
you're a Q expert.
Sorry. What expert?
You're a
I didn't
Q
hear.
expert.
Q. Sorry.
Q. Yeah. So no, because you've discussed queues and priority queues
Q.
for
Yeah, Q. Yeah, Q.
Q.
Oh, thank you. Thank you.
Okay. Sure. Okay. All right.
Yeah.
Yeah. Thank you for your
That's an
presentation.
interesting topic. And yeah, by the way, next time I'll search for another topic, another data
Okay.
structure. We'll move to
Uh-huh.
another data structure. Yeah. Yeah.
All right. Okay.